Our next presenter is Wai Ming. He's also working with Dr. Kim, and his research interests are in wireless communication and statistical signal processing. And he's right now working on interference management in the 5G physical layer. And with that, we welcome him.
Thank you for the introduction. I'm Wai Ming, a second-year PhD student and working with Dr. Kim. Today, I will present my work on the frequency hopping pattern design in the 5G new radio channels. So before starting, we will introduce what is the 5G new radios. With introduction of 5G cellular network, it is designed to support the requirement for supporting stable data rate and support massive user and also with high reliability in the communications. So in the 3GPP group, they define the standard of this 5G network, and they, in order to support this requirement, they define the 5G to using in three generic use case. First use case is part of the 5G network will use supporting this and has mobile broadband side. This is in order to provide a stable connection and with high peak data rates, such as we do streaming in the mobile phone. And second slide is to support the defined as the ultra reliable and low latency communications, ULRLC. This slide will be enable the low latency and high reliability communication, such as the self-driving car. When they connect to 5G, they require very low latency. And the last use case is the massive machine type communication, MMTC slide. This one is in order to support the massive IoT device, and which sending the small data payload, but the number of users is much more higher than the another two slides. So in support this three use case, the 5G will divide the frequency and time resolved into the spectrum into different area to support these three cases. For example, the first EMB slide will require a small amount of frequency bandwidth with and in the lead, they divide the frequency spectrum to square of this two resolved band. And for second case, ultra reliability low latency communication, we divide the frequency spectrum to allocate the whole bandwidth, but with small amount of time. And the machine data type communication, they require much small amount of frequency spectrum, but they occupy a much longer period of time. So, however, to be more specific in 5G application, like apart from commercial use and defense application, also will consider using 5G network. So we need to consider more practical consideration. For example, in the war field, we have different types of device, like the soldier has their Android device to communicate with the tactical operation center, and also they need to control the drones. So to support these different types of device and with different requirements, and their communication will sending this intelligence, surveillance, and reconnaissance data, ISR data in different environments, such as urban, field, or mountain operation. So in this case, the 5G application will will be have to consider the security criteria. So it is critical to achieve DoD mission. So, however, in 5G standard, there's still a lot of vulnerability when we apply this in military missions. Because those ISR security data, if they standing to current 5G network, they are exposed to different kind of malicious entities. For example, the first case of attack is if there's some fake base station, they can performing DOS denial of service attack to preventing our soldier or drones cannot get the sufficient quality of the service. Also, the fake agent can easily perform battery draining attack that will have attack those like drones, especially to kill their battery and they cannot perform the operation. Second type of attack is man-in-the-middle attack. Because the 5G network is using a wireless level of communication. If the attack can sensing the data before, even between the level of transmitter receiver, they can do the data following attack and also selectively drop some packet. So it's also very critical in this DoD application. The third type of attack is to learning the ISR data and to locate our war fighters. After learning those data, the attacker can send those data to the ambush and they may harm our soldier easily. However, this kind of attack is very difficult to prevent because mostly they are at first where they just mixing the passively receive the data and our legitimate user side is difficult to locate them. So if in the whole picture of this end-to-end network, if any one of the link is compromised, the whole security chain will be broken. So why we consider this problem now? Because the DoD Advanced Operation decide to sharing those ISR data with high bandwidth substantial drone need to send out the image and video data. But in 5G, we can support sending those mobile data streaming in real time, but they didn't consider much on the security. And also DoD it's difficult for them to leverage the commercial 5G for they cannot fully rely on the commercial 5G because with insufficient security. So also DoD cannot rely on the slow PGPP development timeline. We have to address them in a timely manner. If we don't, those ISR data sharing will be exploited by enemy and result in catastrophic consequences that motivates our programs. So basically, we are considering how to protection on the physical layer. It's the whole picture of our protection scheme. In the application layer, we will do encryption, and after that, we passing those data to physical layer, and we do another encryption with tag, and also do standardized encoding. After those encoded data, we will pass into moderate by OFDM, and we also after that we do frequency hopping and low detection or detection communication and coding, and then we transmit those data. If those data is attacked by middle, we detect state because we do frequency hopping and we also already enhance the protection from the toxic and eavesdropper, and also if the German attack with our protection scheme is the German is become more difficult to attack our data. So this my work present here, we focus on frequency hopping problem. It provides a jamming resilience and also data confidentiality potential. So here's quick review on because we consider the all number of user like the soldiers, so this purchase of the use case of the 5G slide is MMTC. So in MMTC, it allow 5G MMTC allow the we do frequency hopping. What frequency hopping is we every time slot we will change our frequency usage expression from hop to hop. So this in each hop in each block we will the data will contain data block and also reference signal. So the MMTC data device sending small payload with on and off period. With frequency hopping, we allow more flexible pattern allocation and prevent wasting the result efficiency. And also later we show also prevent the interference from the attacker. So here is more is illustrating example of our formulation of frequency hopping. Usually static frequency hopping pattern is used, but it will suffer interference by the enormous MMTC user because the attacker may learn our pattern and then they can attack correspondingly. Like for in this picture it shows, initially we do linear frequency hopping, but if the attacker learn our pattern, they can attack our user, specifically attack the user. However, if we do the frequency hopping in a dynamic way, it can prevent the attack by the attacker. Currently, in satellite application, they apply frequency hopping, but they are still using uniform frequency hopping. However, we found that the uniform frequency hopping is not optimal case, for example, for castle band jam attacker. So this motivates us to leverage the interference pattern to design a more dynamic frequency hopping pattern. So here is our problem formulation. We divide the number of we divide the number of hits for each user of their cutting their frequency hopping pattern. And also we consider the SINR signal to interference plus noise ratio. So our design criteria is we want to optimize the minimum, we want to optimize the worst case SINR, that is to ensure the quality of service in terms of fairness of multiple users. However, we find that optimize this worst case SINR is complementary, is intractable. So we show that we can alternatively solving the number of hits of the pattern. We can we minimize the maximum of the number of hits between each pattern. It can be solved in a much lower complexity compared to the original mass mean SINR. And also in practice, we don't know the exact use attacker pattern. We have the statistic of the attacker pattern, so we resolve to optimize the expectation of the number of hits between each pattern, the user pattern. And we resolving this optimization to design our pattern for all users. So here is the simulation result. We can see our proposed scheme, although it cannot achieve the there's a declaration from the attack-free scheme, but our scheme can show outperform the existing uniform frequency hopping pattern scheme. And also when we look at the peak error rate, we can see we can guarantee that 80% of users, their performance is very close to the attack-free cases. So yeah, to conclude, our work, we addressed one of the vulnerability in the military mission 5G. We provide a preventive measure of the adaptive frequency hopping in the MMTC for jamming, receiving, and data confidentiality. The current uniform frequency hopping is used in current satellite, but it's not optimal in the 5G use cases. And then our solution, we leverage interference statistics and to design our adaptive frequency hopping pattern to further improve the reliability. Okay, thank you. Any question?
Thank you. Question?
Like, can you go to your organization problem? Is
Yeah.
How do you solve this?
Yeah. Yeah. Once we simplify to this form, and then we further using greedy manner to solve the this maximization one by one. Yeah. Although the greedy manner is not optimal, but in our numerical simulation, we can see it can have very close performance to the optimal case.